Good morning, everyone. My name is Henry Jacob with HRAC Consulting Services. I'll be moderating today, and I'd like to welcome you to the Unconventional Challenges and Solutions webinar, a glimpse into the difficulties of enhancing the potential of your reservoir and the keys to evaluating optimization strategies, featuring Craig Cipolla and Cipolla and Ohm Lorwongngam with Hess and Ahmed Attia with Ziebel. I think you'll find the presentation very interesting, and would like to thank Craig and Ohm for their willingness to share a lot of the great technical work they've done. So welcome, Craig, Ohm, and Ahmed. I'd also like to introduce Rob Porter, President of Ziebel, and Michael Sparacino, Vice President of Technical Solutions with Ziebel. They'll be on the panel. And today's webinar will be led off by Craig, followed by Ohm and then Ahmed. Craig and Ohm's presentations will last about 15 minutes each. And Ahmed's presentations is pre-recorded, will last about 10 or 12 minutes. Following the presentations, I'll have a Q&A session, giving you the opportunity to ask Craig, Ohm, and Ahmed any questions you may have about the presentation. You can ask the question by typing in the question in the chat room. If we run over on time commitment, we'll continue the Q&A session for those who wish to hang on. So I'd like to go ahead and get started and introduce our first guest speaker, Craig Cipolla with Hess. I've known Craig a long time. He's always been at the forefront of technology in the hydraulic fracturing and now the unconventional world. Craig is a principal advisor on the Hess technology team, provides worldwide support on hydraulic fracturing, completions, and reservoir engineering. His current and long-time focus is on optimizing unconventional resource development. Craig has co-authored over 75 technical papers, has served on the SPE Distinguished Lecturer on Hydraulic Fracturing, and was a recipient of the prestigious SPE International Completion Optimization and Technology Award. So with that, Craig, I'll turn it over to you.
Okay. Well, thanks for the flattering introduction. Appreciate the folks at Ziebel inviting us to speak. So what I'm going to do is talk a bit about fracture geometry, conductivity, and drainage area. And a quick outline, I'm going to spend just a few minutes on conventional versus unconventional thinking, outline some of the issues we deal with, talk a bit about where is the proppant. So I think that's something that might be under-evaluated these days. And then a bit about created, propped, and effective length. And spend the bulk of the presentation, however, on fracture diagnostics. You know, what's in our toolbox? I'm going to use some Bakken examples to kind of help us understand this. And then move on to some big picture issues and the future vision, which is just a simple slide to kind of paint what we think the future might look like. So we'll go into the conventional world, and many of us have worked in this area where the standard ways we think about fracturing work. More fluid equals more fracture area or length, more proppant equals more propped area and conductivity. We use larger proppants for more fracture conductivity. We use stronger proppants for higher fracture conductivity at higher stress. And really, proppant transport may not have been as unreliable as it is maybe in unconventional worlds. Then we go to the nano-Darcy world. And the more fluid and more fracture length or area, at least, it still seems to hold. But we see a lot of things that are really specific to very low permeability rock. Use of 100 mesh sand, use of smaller proppants, use of low quality proppant, local sands. And I've successful use of these. The testing of micro proppants, very, very fine mesh proppants. The fact that unpropped fractures actually might produce or contribute to production. And then proppant transport, I'm going to show a couple slides here next that suggest that maybe proppant transport's a lot more complex than we think, at least in the hard rock and nano-Darcy world we're working in now. So these are some slides I borrowed from the hydraulic fracture test site 1 in the Permian. Thanks, they've been published. thanks to the folks there. And you can see some very interesting things here. You see how hydraulic fractures can interact with natural fractures, creating a complex system here. You can see the walls of the fracture can be very rough. You can see that you know, the proppant, there can be multiple fractures initiated, maybe at least at ahead of the fracture tip, and how the propped height might be affected by bed boundaries. And we've seen lots of papers on layering and layering effects, lamination effects. You can see some of these in a little bit bigger scale here, how the proppant's kind of stuck in these complex areas or trapped. How these rough surfaces, these fractures might lead to unpropped conductivity. Just a little shear offset and a little roughness can lead to relatively high conductivity, at least initially. And then again, this expansion of the bed boundary here, how that could easily trap proppant and maybe even affect fracture height growth. So a lot of complexities we have to deal with. And the issue here is, what do we do to try to understand some of these complexities and understand better our fracture performance? So that gets us into this discussion of created, propped, and flowing fracture lengths. For a long time, we've had microseismic data to help us understand created length, and I've used other measurements because there's a lot of things coming up now, you know, the strain and the various types of pressure measurements that are helping us understand fracture geometry. And on the right-hand side here, I've given an example. It's by no means an exact model, of course. It's just an example of, well, if we have 1,000 foot that's created, what might be propped? And most of the time, there's very few direct measurements of propped area, and for sure, none that actually sample the whole propped area. We use models. So we use our fracture models to estimate where the proppant is, and that might be 200 to 600 feet. Just pick a number, but less than the, or probably less than the created length. Then here comes the most controversial subject, is flowing lengths. Okay, those flowing lengths we would estimate typically with models, very few direct measurements, although I'll show some of those. Maybe detailed reservoir simulation models, maybe rate transient analysis or other types of analytical techniques. And the question here is that those techniques and other simple models might suggest that your fractures are 10-foot flowing or all the way up to 1,000 foot. This is a huge range, and it significantly affects our optimization process, both in cluster spacing and in well spacing. So this is an area I'm going to spend a little bit more time on in the last portion of the presentation. So the toolbox. We have a lot of fracture diagnostic technologies. I'm not going to read them off here, and by no means is it a complete list, but I've broken them up into 3 different areas. Completion effectiveness, you know, where did the fluid and proppant go? What's our cluster efficiency? What's our cluster uniformity? And where is the production coming from? I'm not going to talk about that, but ohm is. That's one of the key measurements that we always talk about is, you know, are all the clusters producing? And ohm's going to touch on that in a lot more detail. Fracture geometry, simple things, length, height, but complexity, try to understand that, azimuth and asymmetry. And then this other big area of drainage area. What's flowing? You know, what's the conductivity? And in these long horizontal wells, what are the drainage patterns and the variability? So I'm going to use the Bakken as an example here. We've had a long history of data acquisition in the Bakken, covering probably a little bit over a decade now, starting with this is when it was published, by the way, this first experiment here, but the test was actually 2009. So the first thing we did was we started to use microseismic to understand depletion. So MDD stands for microseismic depletion delineation. And we moved on to try to understand our first plug and perf trial, well spacing issues, and a lot of other well spacing and completion optimization trials. And what Ohm is going to talk about is this most recent completion optimization trial or test, and it's highlighted here in number 5, 2 specific areas. And what we're trying to do, again, is gather these pad scale measurements. You can see them all listed here, a lot of detail with the primary goal of calibrating our models. And they could be very detailed physics-based models, hydraulic fracturing, geomechanics, and reservoir simulation, or simple completion optimization models for extreme limited entry. So with that goal, I'm going to talk a little bit about completion effectiveness. You know, where did the fluid and proppant go, and where is the production coming from? Well, Ohm's going to talk about that. I'm going to skip that because he's got a lot of information in his presentation. So I'm going to talk a bit about proppant tracers, permanent fiber, and hopefully weave this into a story of how have all these things fit together to understanding the big picture optimization, not just completions, but well spacing and wellbore geomechanics. And you can see what Ohm is going to cover in his presentation. So typical RA tracer log here, you have 3 tracers, red, blue, yellow, you get iridium, antimony, scandium. You can see here, this is showing tracer in all of our perforation clusters. You can't see the cluster that much, but you can here. 2 tracers here showing proppant was moving through into those clusters continuously throughout the job. And in this case, we're showing 98% cluster efficiency, meaning that they took proppant. Doesn't mean it's evenly distributed. This is not untypical for our Bakken completions with our modern plug-and perf limited entry designs. You can also use drilling data, either just simple drilling data, or you can use accelerometer measurements near or at the drill bit to estimate the rock properties along the wellbore and stress, so get a profile of the wellbore geomechanics. That's what I'm showing here. And you can see in these different colors, there's some variation. This is a typical middle Bakken well. But if you look at the color scale down here, it kind of suggests, which is what I'm trying to illustrate here, there's not that much variation in the middle Bakken, and also not very much variation in the Three Forks. And with this, what we can do, and the companies that provide these services can do this, they can predict what the cluster efficiency should be with your limited entry design and with the net pressures and so forth that you provide to them. And what we see here is the predicted cluster efficiency is 100% with the design that we had provided and this particular mechanical stratigraphy, which is consistent with what we see with tracers. What they can also do is predict how efficient that fluid is distributed. So this will be kind of interesting when we see the next slide. The prediction here is that the efficiency should be about 84%. So reasonable distribution of fluid and proppant, or at least fluid within these clusters, and maybe 16% were understimulated. There's some upside if we could really optimize our perforating strategy to maybe 94% even distribution. But again, what we're seeing here is predictions are that there's really pretty good fluid distribution and very high cluster efficiency. So this is now we're going to move on to distributed acoustic sensing, or DAS, from a permanent fiber. These are some results from a big test that we just completed. And I'm going to show you one example here, and that's on the right. And what we see here is the standard treatment data, the pressures, the rates, the proppant concentration. And then with the distributed acoustics, or the permanent fiber, we can predict, or the provider can predict, how much fluid is going through each cluster as a function of time. That's what you see here. So there's some variation. And then with that, you can predict the uniformity index, which is a measure of how uniform that fluid is distributed throughout that job. And what I find interesting is if you look here, this is the estimation of fluid and proppant through 14 clusters. So this is a 14 cluster stage. And you see some variation, but it's relatively uniform. And the uniformity index is 0.9, with 1 being perfect and 0 being, I guess, I don't even know if you can have 0, but very, very low. So in this case, it's extremely high, and it's also a relatively high cluster count. And what we found with all these measurements is 100% of the clusters were stimulated. We also found that 84% uniformity with 7 clusters, and about the same uniformity with 14 clusters. So we got some confirmation we could pump jobs with higher cluster counts. It decreased to 72% with 18 clusters, so maybe some improvements possible, not maybe, clearly. And maybe we can do this with tapered perforating, which we were able to shift from heel to toe bias, from toe to heel bias, just by tapering the perforations or the perforation design, and higher limited entry pressures. I think Ohm will talk a bit about that. There was lower uniformity with diverters, which we found to be interesting, at least the way we applied it. So we're focusing on the limited entry design to increase our number of clusters, which will save us money and optimize our uniformity. So now let's move on very quickly. So as you can see, I'm covering a lot of stuff fairly quick here. So nothing in detail. Up to hydraulic fracture geometry and drainage area. So I'm going to talk about geometry measurements with microseismic strain and offset well pressures, and then drainage area with MDD, or microseismic depletion delineation, and offset well pressures and defits. So we're going to go up here to this number 4 project, the RS project, which was actually published at the 2020 Hydraulic Fracturing Conference. And it's basically the same type of work we typically do, except This has some unique characteristics, which you'll see next. One of them is time-lapse defits. So in this project, which was really performed for a propane injection EOR project, which was, those papers were published at URTeC this year, is you had a older horizontal well, which you can see the completion down here. It was a slotted liner with a single stage job with a whole bunch of ball sealers for diversion. Actually looked like it worked okay. And we drilled 2 vertical wells here. V1, which was fracked, and we did a defit. The V2, which was used for microseismic acquisition and tiltmeter acquisition, which I'm not going to show. And we drilled them on azimuth. So you'll see frac azimuth is in this direction. And what I'm going to focus on here is some of the initial work we did before the EOR injection. We shut this well in, ran a bottom hole pressure gauge, which you see here is about 750 to 1,000 psi. It doesn't build up much in 30 days, so it's pretty decent depletion around this wellbore. We did a defit in the V1 well. You can see that defit hits the H1 well right here with only a 20 barrel defit 1,000 feet away. And then we pumped the MDD, which you'll see later, into this well to map drainage. And then very quickly after that, we fracked the V1 well and then returned the H1 well to production. So the first thing is to look at how we can map drainage with microseismic. So this is the MDD outline. Again, we pumped about 10,000 barrels of fluid, 8 barrels a minute. And you can see the outline here, about 500 foot of drainage around this well. Maybe a long frac here at the heel, which is not all that unusual. Again, 1,000 psi here. And the defit that we did in the V1 well prior to this MDD, remember, was 1,500 psi, which is essentially initial reservoir pressure. We did a lot of modeling here, which is highlighted in the publication, that suggested permeability to oil. Even though this is microdarcy matrix rock, permeability to oil was about 65 nanodarcies, and the prop fractures were, not unusual, 40 millidarcy foot initial. Unprop fractures, which we include in our models, were 1/4 millidarcy foot. So first of all, once we had that, and then we went in and fracked the V1 well. And that's what you see here on the lower left-hand corner. The kind of interesting thing here is 2 things. It's a 1,000 foot long fracture. It's also very symmetric from the V1, 1,000 foot in this direction, 1,000 foot in that direction. And we also saw that we didn't, it looks like the pressurization of this H1 well is what resulted in this more symmetric frac. But the most interesting thing here is that we went into this V1 well after about 2 months, and then went into the V2 well after about 3 months of production from the H1 well, which you can see here, okay, about 3,000 barrels. And we did a second defit in the V1 and an initial defit in the V2. And we saw 4,000 psi, remember about 1,800 psi depletion in the V1, 4,800 psi in the V2, so 1,000 psi depletion. And the production from the H1 well was doubled, okay, primarily we think due to this frac hit. So we're flowing fluids from 1,200 feet away all the way into the V1 well with a relatively crappy frac with 15,000 pounds of proppant that's spread over, a total length of 2,000 feet and a total height of around 300 foot or so. So it gives us a direct measurement of flowing fracture length, which is considerably longer than we might have estimated just based on simple models. And it's a direct measurement. So we have 1,800 psi depletion in 3 months, and that depletion has to be coming from this oil flowing into the H1 well. So really, really important information to help us calibrate our models and understand basically what bulk fracture conductivity looks like. So I'm going to wrap up here with a couple more, one more example and just a couple slides here. We are also really trying to understand drainage between Middle Bakken and Three Forks and how the drainage patterns change along our wellbores. So we've have an ongoing project. It's an observation lateral project. It's right here in red, where we have drilled a 10,000 foot dedicated observation well with 30 annular pressure gauges and fiber. Offset to that are 2 Middle Bakken wells. One of them is completed with fiber and annular pressure gauges. And that fiber, of course, was an example of what you saw previously. And we also instrumented the other offset well with microseismic. You can see kind of a plan view here. And the goal here is to map Middle Bakken to Three Forks drainage and also the drainage patterns from heel to toe. So it's a very, very interesting project. I'm going to show you just one example of some of the data from that project. What you see here on the right is a map with all these yellow lines of all the frac hits that were recorded on fiber, both in pressure and with strain. And here you see an example in the middle. We'll start here at the bottom. You see rate, pressure, and proppant. And here comes the proppant up here is the pad portion. And right about here, these pressure gauges start to react. Okay, so this is the pressure. This is a frac on the H5. These pressure gauges, what you're looking at, are on the H4 here, and they start to react right about this time. And it's also corresponding to the same time you see the fiber. So this is depth, and this is time. This is the frac approaching. So you see the tensional effects here. Then you see multiple fractures crossing that particular H4 well at that location, showing us a bit of the fracture morphology, or how many fracs are created in the H5, how many fracs are propagated in the H4. So we're just in the initial stages here of understanding fracture geometry and getting these detailed pressure measurements. We're just now entering into the interference testing phase. So really interesting stuff. So last two slides, just take a quick step back. I've been talking a lot about these pad scale measurements and calibrating our physics-based models. But really, what's the whole point? The whole point is field development optimization, well spacing, completion design. And at the same time, we're working with 15,000 plus wells in the Bakken, doing a lot with all kinds of data, putting that into big data, predictive analytics models, and also forecasting results and doing optimizations. Neither one of these tools will give you the best answer, but when you combine them, you start to get a relatively clear picture of what the optimum spacing and completion design will be. So we're trying to combine the analytics with the completion, with the physics-based models to optimize field development. And then the last thing is, where are you trying to go? So we're somewhere like this now. I mean, I'm not saying this is the exact Hess development. It's not even meant to be. It's just a cartoon. But if we're here now with a number of wells per drilling spacing unit with 30 stages and 300 clusters, we might be fracking all the clusters, and we might be getting reasonable fluid distribution, but we still might not have the perfect development strategy and the perfect drainage. What we really want to do is we really want to develop the Bakken with a whole lot fewer wells, with very long effective fractures that are perfectly spaced. So this is the goal here. And again, it's not meant to go from 8 to 3. It's just meant to give you a mental picture of what we're trying to do with all this data. What we're trying to do with all this data is find out how we can make fractures more effective, drain more area, and develop the Bakken with fewer wells that are more productive. So with that, a lot of people to thank. Of course, I present a lot of data that Hess Corporation supported. The Hess Bakken team, of which Ohm's a key member, did a lot of this work, and without them, we wouldn't have any of this stuff published. And then Halliburton, Pinnacle, they did all the microseismic fiber and downhole tilt measurements, which you didn't see the downhole tilt, but it was really quite interesting too. So with that, I'll turn it back over to Henry, and we'll see what Ohm has to say. Thanks.
Great. Thank you very much, Craig, for covering that very interesting material. And I know you'd like to have more time to go through that, but some of you guys are doing some really interesting work in the Bakken. So thank you for that. Next, I'd like to introduce Ahmed Ohm Lorwongngam. He goes by Ohm. Ohm is Completions Engineering Advisor for the Hess Bakken Asset Team. Ohm has been with Hess for 12 years and is responsible for all development wells in the Bakken asset, from the planning and design phase through the flowback operation. Ohm has a wide variety of experience. He's worked in the Permian, Gulf of Mexico, West Africa, and Bakken, so he's seen a lot of different types of reservoirs. Ohm received a master's degree in petroleum engineering from the University of Oklahoma. Ohm, thank you for your willingness to share this data with us, and I'll turn it over to you. Thank you.
Thank you, Henry. Thanks, Craig, for the setting it up. Let me share my screen really quick. Okay. 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 Give Maybe 1 minute poll. Okay, so basically, what am I going to show you here today is just a little part from what Craig is showing, right? This is a extreme limited entry design completion. How do we improve our productions and lower the cost? So this is the paper from URTeC this year. We have a lot of people here, so you can see that I'm the first one, and Craig is the last one as the editor-in-chief, what they usually call him. So next, the objective of this paper or this presentation is to show that the case study of using extreme limited entry design in the Bakken area. So we're going to be using some geology and engineering type of diagnostic to understand the higher limited entry pressure. The background here, as you can see, this is the two diagnostic pads that Craig mentioned. At that time, we want to explore ways to reduce cost and increase production. And XLE design came up, and we want to try out it. So now we want to be able to prove it. The two pads, as I mentioned, are the SCDSU and CADSU. So before we get going, so for those of you who might not be familiar with extreme limited entry, so essentially what we're trying to do here is we're trying to reduce number of holes, make the holes smaller for the perforation holes, and with that we want to be able to distribute the fluid to make beautiful pictures of perforations that Craig just showed us in the last slide that he just shown there. So this is nothing new. Limited entry pressure has been around for since 1963, but really the concept of extreme limited entry started by Paul Weddell with Liberty or Weddell since in 2018. So he said just increase your limited entry pressure 1500 to 2000 psi. You're going to get good distribution. And the thing is, we want to take it and try to prove it with our own different type of diagnostics that Craig mentioned. Real quick on the cluster efficiency. I'm going to be talking about cluster efficiency a lot, and that means a percentage of stimulated clusters over total planned clusters per unit of measurement. Okay. On your right-hand side, you have the perforation cluster. Perforation friction calculations. Essentially, is the Bernoulli equations that's really showing that these terms that I highlighted, these are the terms that, as a completion engineers, we can control. But the biggest term that will affect is the diameter, which is times to the power of the fourth. So it's very, very important on your limited entry. So what you will learn today is that extreme limited entry design is proven in the Bakken with multiple type of diagnostic data, and we will be able to capture more than 90% of the cluster efficiency in all of these type of diagnostic. We were able to achieve stage count reduction from 4 to 12 stages, and we were able to maintain production. That's really allow us to save about 10% or more in some wells and some costs. That's a lot of money that you can save in this type of environment. Okay, 70% of the stages show heel-to-toe bias. So you're going to see that quite a bit from the downhole camera. XLE design used in this paper, we found that it results in that effective completions. we were able to find it's effective completion despite of geological heterogeneity in the Bakken. Okay, the most eroded perforations found the loci. I think we saw that before. I want to mention another thing is QA/QC of these perforations are very important for us to be able to get that high limited entry pressure. For some of you who are not very familiar with the Bakken, this slide just shows you that the Middle Bakken is the main formation that we refract and then we extract oil from. We also have the Three Forks, which is a little bit lower, which is thinner, about 50 to 40, depends on the area. But in this case, Middle Bakken generally, it's going to be a main and a thicker. Within the Middle Bakken, we have sub formations, which we will not be touching in this presentation. Let's move on to diagnostic data gathering. So as I mentioned before, we have two pads, okay? Two pads, and two pads. One is called SC, another one is called CA. The wells that I highlighted in red here are the wells that we did the data gathering on, which means we run some diagnostic, we run fiber optic with Ziebel, we run RA tracer, which I will go over just a little bit on the results. But on the completion side, you can see that on the SC wells, we pump 18 million pounds, 360 clusters per well, and they all have 48 stages. So which means that at that time, we were working on what we can do to reduce number of stages. So, so at that point, these well limited entry pressures are about 1500 psi in the HEO stages. Now, after the success of the SCDSU, we want to confirm the result by using the CAH5. So on that well, we pump 12.8 million pounds, 320 clusters. Now, at this point, we were able to reduce the number of stages from 42 in some other wells in the same batch down to 29. So that's what, 13 stages that we were able to reduce, and then we save a lot of money that way. And the productions chose to be in the same way as well. These are the maps of the 2 DSUs. So real quick on the data gathering that we did in these 3 wells. Okay, as I mentioned, we did prop and tracers. Okay, this is the tracer that Craig mentioned. I will not go into detail, but what we did is we just pumped it during the frac, come back and log it during coil tubing operation. As Craig mentioned, we usually use it as yes or no. Something went there, something perforation went there, something left there. We go and found it. It doesn't give us any quantifiable as far as how much. Post-fracture deployable fiber optic. This is the Ziebel product that we used. So this is a carbon fiber rod. I think the next presenter will go into more detail. Essentially, we use a DTS and DTS to interpret for cluster efficiency, and we ran it about 3 months after the first oil. We also ran downhole camera in the CEA wells, and we also used step-down tests to help us verify the limited entry pressures. So the cartoon on your right-hand side here is showing you how far the fiber optic were able to reach in the well. So in this case, without the tractor, we reach about half of the lateral. We run the IA tracer in every other stages. Okay, same thing as the SCH2, very similar. And then on the CAH5, again, this is a confirmation of the success of these 2 wells. We ran camera data as well to understand the difference, and then the fiber optic data. Okay, these different colors shows you how we ran our perforations. Our clusters design. You can see that we ran some 15 clusters per stage in between 8. We just want to minimize the changes in the in geology, and then after we come back, we run a Ziebel fiber optic to understand the information. Okay, so some results on the prop and tracer. You can see yellow is a scandium, red is iridium, and blue is antimony. You can see we got very, very good cluster efficiency based on the tracer data. The same goes as the CAH5. However, one very important thing in the CAH5 we found was we had a couple of plug leaks, and that it's really taken effect on the numbers. So we found that if we have a plug leak, our cluster efficiency by using our tracer dropped quite a bit. So compared to other wells that we were able to get up to 92% and 95% with plug leakage issues, we drop it down to 77%. So that's quite a bit. So this is a very important piece. Next, the step-down test results. This slide just really show you that step-down test is an easy way to measure your limited entry pressure. Okay, what you do is you just tell your treater said, hey, drop it down. Once you get up to rate before you start your sand, then do it again at the end to understand the limited entry pressure before and after your frac. Okay, so just drop it down 4 steps. I'm not going to go into detail how I calculated here. We have another gentleman, Mike McKinney, who did this work for us. He interprets and shows that the perforation friction, okay, on your left-hand side here, this is the pre-frac. Okay, this is post-frac. So pre-frac, the blue line shows you the per friction number, okay, and the bar shows you holes, number of holes open. Clearly shows that the blue line, pre and post, are going to the right directions, which means that we were able to maintain our perforation pressure. Maintain perforation pressure give us a good indication that we were able to maintain our distribution in the perforations. Okay, number of holes open in this well, we run majority, well, all of them should be 2 shots per foot. So we can say that if we can get more than 50%, we know that we have a chance to get 100%. Again, this is just, for me, this is just way to verify your limited entry pressure. And to be able to get a good cluster efficiency, we would need to use a fiber optic data. So let's move on to the fiber optic data. This fiber optic data, I will not go into detail. I think the next presenter will go into detail. Ahmed will do that. Really, what I want to show you here is the different tracks that we get from Ziebel. Number 1, 2, and 3 are the DES and DTS data, and then they use the information to interpret for ranking. Essentially, that's if that cluster is producing or not. And then the water and oil are separated by using the plated model. Okay. So if I zoom in into the last 2 stages of SDH2 well, okay, we can see that this red line here represents the temperature. Again, this is very important to mention. This is only 2 or 3 degrees here, 3 degrees. So we have 3 degrees dropped. So we know that the lower in temperature indicates injection. In this case, this DTS line is showing that we have good injection within the stage. Our production is good as well in this stage with 15 clusters. And that information matches well with the RA tracer data. Okay, 15 cluster works for us in this case that I'm showing you. However, in this 8 clusters per stage, we have 1 cluster that did not produce. Okay, so just a summary for RA tracer data. So we did that on all 3 wells. As you can see, for example, the SDH2, the red highlighted wells are the wells that, stages are the stages that we use extreme limited entry design in. And you can see that it's 100 to 97 cluster efficiency. Now, if you go back and look at all this information in the table on your right-hand side, you can see that the average that we obtained on all the wells are above 90%. So that's looked really good for us based on this data from Ziebel here. Next, we also ran some dial hole camera. I will not go into detail, but you can see that majority of the camera pictures show that the biggest, largest hole at the bottom, this is coming from, the mother nature, right? This is, you can't fight the physics. So physics is real. So that it's a gravity effect. So you can see that it's showing that biggest hole right there. This is a very important piece of information as well. I want to show you that QA/QC is very important. So this type of bar charts, this is toe, this is heel, okay? We show this type of bar chart, we show you the erosion per stage, okay? That, as I mentioned earlier, we have heel to toe bias. So we have majority of the heel erosions more than the toe. Okay, this happens a lot. About 70% of our stages that we obtain. Now, we found one stage that we just see that this type of bar erosion is actually larger. When we came back and looked at it, we found that, as I mentioned, we ordered 2 shots per foot. Now, some of these clusters got 3 shots per foot for whatever reason. And then this is based on similar to what the Bernoulli equation that I show you. We have more holes, we have less perforation pressure. That's going to create runaway clusters. And essentially, we are proven by doing it here. So QA/QC of the gun is very, very important. So really quick on the geology integration. So On the geology integration, as I mentioned in the Bakken, we came back and look at how the wells are landed in sub formation in the Bakken, but we were not able to find any major impact on the cluster efficiency by geology. Okay, we're not going to detail there. There's a paper for the URTeC. I'll let you guys go and read that one. Data integration. So this is very important for us engineers here. I put all the data together. You can find that this is the Ziebel post-fracture deployable fiber optic. This is the RA tracer. This is a downhole camera. Put all three of them together. We see that RA tracer do not directly correlate to production from the fiber optic. What do I mean by that? I mean that the RA tracer just sometimes it doesn't show that it shows that we inject something in there, but it doesn't mean that we always produce production from those clusters. Okay. Now downhole camera is showing you we have highest erosion over here. Okay, but it doesn't mean that we get higher oil production or water production. Okay. So the discrepancy in this result is likely due to the uniqueness of the diagnostic measurement or how we obtain the data. The fiber optic, actually, we measured acoustic and temperature. Okay, RA tracer, we measured some residue of the proppant that's left in there. The camera, we just measured the erosions, and we want to use that to interpret for cluster efficiency. But these three things might not be correlated at all. But one thing that it shows is we got good injections for the XLE. Okay. But another reason would be that some cement uniformity, complex fractures similar to what Craig has shown. There could be some cross flow and some other geologic characteristic that we cannot show here. This slide to sum it all that shows that the XLE, okay, in all of the diagnostic method, XLE shows high cluster efficiency in all of the methods here. However, want to point out that step down test is good to do for confirmation of the pressures. Okay. Same goes as the downhole camera. We've got high cluster efficiency there as well. So in conclusion, XLE design is proven to be successful, and we get more than 90% cluster efficiency in this case in the Bakken. Operator achieved stage count of 4 to 12 clusters, and we were to save 10% or more in some case. Using XLE design described in this paper, we found that it's not as it's less effective based on the geology. So geology is not affecting XLE injection that much. Okay. If the design limit entry pressure is reached, you pretty much know that you get good cluster efficiency based on our data. Quality control of perforation is very critical for XLE success, as is shown in the last slide. Good data agreement for diagnostic data for XLE. However, is less agreement for perforation erosion data and cluster productivity data from fiber optics. So there is additional work needed to be done to understand the correlation between erosions of the data, of the erosion of the camera, or the volume from the proppant. I'm sorry, and volume of proppant inject. So plug leakage is one thing that that's very important for us. We found that we have some plug leaks, so make sure we get a good plug program. Step down test is a good way if you don't want to spend any additional capex on diagnostic. This is the easiest way to do a XLE strategy with running more step down tests in your well to understand that you have good limited entry pressure. And in this paper, we show that high XLE pressure equals to good cluster efficiency. So acknowledgement, I'd like to thank Hess Corporations and send a special thanks to Matthew Lawrence with Ziebel for helping out to write this paper as well, Christian Girdle and a couple more people, as you can see there. And with that, thank you. I'll hand this over to Henry. Thank you.
Great. Thank you very much, y'all. for sharing a very interesting day with us. The final speaker will be Ahmed Attia. Ahmed is a principal reservoir advisor who leads the Ziebel Reservoir team in acquiring, processing, and interpreting DAS and DPS data. He has a strong sense of leadership. Ahmed builds a culture where employees at Ziebel are passionate about learning, teaching, and applying their technical skills. Ahmed has over 10 years of experience in the energy sector and is focused on developing in-depth understanding for unconventional wellbore behaviors and completion design. Ahmed?
And my name is Ahmed Attia. I'm the Principal Reservoir Advisor for Ziebel. Today we're going to talk about intervention-based fiber optics with carbon rod. This is our unit. Get a mouse out here real quick. And the carbon rod kind of sits on a reel. And you can see it goes up into the gooseneck, into an injector, and into the lateral. So again, this is the dip-in fiber optic conveyance method, which is a carbon rod. And this is our unit that's going to be sitting on location. You can see it's a very small footprint. All we really need is a crane, some lights, and a man basket, and a couple of tie-down points for the injector. Taking a look at the carbon rod, it's 0.6 inch in OD. It's very strong. It has about a 20,000 pound pull force. It's very light. It only weighs 188 pounds per 1,000 foot. And very important, it's very highly sensitive. So anything that touches this carbon rod, sound or temperature, the fiber will pick it up very fast. It has 5 fiber optic lines in it and a coax cable around this FIMP that can power on a tractor and get us out to long laterals, such as 10,000 foot laterals or so. To kind of give you guys a look at the scale, this is a 2 7/8 inch tubing. This is the ID, about 2.441 inches, and this is how the carbon rod would sit in it. You can see there's a lot of room for production and wouldn't really affect the flow as much as a 1.5 or a 2 inch coil, which really impacts how much flow is able to come up the tubing. And most likely, if you were trying to record any kind of flow allocation, you would not be seeing the realistic values of those recordings. On the bottom of the rod, there's a BHA. It's about 1 inch in OD, and at the very bottom, there's 3 sensors: the temperature, pressure, and a triaxial accelerometer. There's capability again to add on a tractor here and pull the carbon rod all the way to TD if you desire to do that. We're going to get into our applications. Our first application here is our flow illuminator. And what that's going to help you do is really understand your completion optimization and your flow allocation. And I will talk about that just briefly here. So on the left-hand side, I'm going to go through my tracks real quick. On the left-hand side, as Ohm was suggesting here, this is your temperature track. Your red is your shut-in temperature, and your blue, and if you have other colors doing other production tracks, such as your blue, green, and yellow here is your production tracks. Those are your temperature traces. So if in red, if you were looking at this without any other information, you could see, well, the only other information, let's say, you would have is your completion analysis or your completion diagram, which is right here. Each one of these green lines here is a perf. If you were to just look at that, you could say, well, each one of my clusters has a cool spot indicating some cooling happening at each of the clusters. The only one that's doesn't have any cooling is this top one. Well, that could be looked at in 2 different ways. One is, hey, maybe that warmed up because it's a very strong producer and it produced all the coolant back or all the frac fluid back, or maybe it's just didn't get any stimulation fluid at all and it's just not performing. So you do need a second form of information to really constrain your temperature model that you do, and we do that with acoustic data. This acoustic data here will indicate to you what clusters are performing, how strong they're performing, and also give you an idea of what phase composition they're holding. So in this particular differential acoustic plot, you can see that all your clusters are performing quite well, except that top one there is not performing at all. And with that, we have something called a producing cluster efficiency, and that's 7 out of 8 in this particular case, which is an 88% producing cluster stage. We're looking at one stage right here. If you're looking at effective clusters, and what we try to do is, again, as Ohm mentioned in the previous presentations, we rank this. We rank it by the acoustic signal coming out of each of the clusters. And you can see if it's a rank 1 or lower, we deem it a non-effective cluster and give you another track to kind of look at, and then that's called the effective producing clusters. and that in this particular stage is only 75%. The next application is the frac illuminator, and this will help you understand well spacing. So well spacing is quite important. A lot of people can see that with pressure at surface or just through production, they turn off the well adjacent to the well in question and they see their production go up or down, or they see a pressure kick, but they really don't know, is that interference happening in the heel, in the toe, across the lateral? Is it through a geological feature? What exactly is happening? So in acoustic data and temperature data, it can give you a lot of those answers. And this particular example right here is a great one where it can show you, if you have all your wells on your pad on, then you're actually looking at this track right here, where your last 9 stages are not performing at all, and the top stages here are performing pretty good. So that's when your offset well is on. The second we turn the offset well off, all the stages, those 9 stages that were off, come to life. You have a very strong influx of production coming in here, and the rest of the lateral that was doing okay is actually doing great now. It's being lifted. And what they found was their particular clusters were actually connected through a fault, or sorry, the particular wells were connected through a fault, and in turn had a huge effect on the lateral. So yes, they did see it in production numbers. They saw it quite strongly, but they didn't really understand, is that through the geological feature? Is it happening throughout the entire well? What exactly is going on? So with this analysis, they can see, yes, it was through a geological feature. You can easily see it in DTS. You can easily see it in acoustic data, and it has an impact on the entire well. The second part of frac illuminator is the FDI and microseismic events. So if we're in, let's say, a parent well, or we're in a child well that's not perfed at all, and we're fracking the adjacent wells next to us, we can pick up both microseismic and also any kind of fracture-derived interaction, whether it's a frac hit or any kind of pulse from pressure. We can pick them all. We can pick all that up. So we will correlate your microseismic to your FDI events that happen in the lateral, and this is what we're seeing right here. This is an event that happened at a stage. And lastly, this last example is a crosswell strain example. This particular client what had us in the parent well while they were fracking the child well. You can see here on the bottom section, this is your child well, and then the parent well we were in is this top well here. They were fracking in stages 46 through 51. We're hitting the parent well at stages 43 and 44 over and over again. And it wasn't until stage 52 that the frac started going in the right direction. So you can see there was a huge gap right here that kind of indicated that most likely there was some missed rock, missed production, something happened here that definitely the client needs to take note of. And maybe if there was any kind of possibility to make any adjustments real time, then that's something to look at. So we can actually also start, we weren't able to do it in this particular example, but we are now, with technology growing, actually be able to stream this live. Stimulation allocation and analysis is our third application. And basically what this helps you understand is how your stimulation went in the well. So we do that by a stimulation disparity index, where the 0 line is basically telling you every single one of your clusters is receiving the same amount of fluid, stimulation fluid, that is. So, of course, that's never really the case, as Ohm showed in his paper and showed in his presentation. So we do have this stimulation disparity index to show what exactly happened. And this is something you can kind of correlate with camera. However, camera really shows you what's going out of the wellbore. What this is showing you is where your stimulation fluid is actually sitting in your reservoir rocks. A little bit different, but it can kind of correlate. In this particular example, you can see the heel is taking a lot of stimulation fluid, is doing really good, has basically a strong presence in stimulation. Where in the toe, maybe the fracs were not as big, didn't really show a weak, or didn't really show a strong stimulation presence. It actually showed a weak stimulation presence, and you can really see that with the stimulation disparity index, as well as the DTS plot here, where it's a lot warmer. Second part to the stimulinator is isolation integrity. So as Ohm said, you definitely need, leaking plugs or bad cement on the backside have a huge impact on production. We can definitely see that on a lot of wells that we record. So even if you're in a well where you're sitting in really, really good rock, and this is okay rock, and then again, you're back in that good rock, and you're producing very well out of that good rock, if you don't isolate your stages 100%, you can have some runaway fracs going into different stages, not really performing in the area that you're trying to stimulate. And then that's what this red box here shows. It shows you an area where you have very good rock, very poor production, and the rest of that good rock is doing good because everywhere else it did, they were able to isolate it and give good stimulation across the lateral. The fourth application is inject illuminator, and that's really to help you understand your injection distribution. So injection analysis is part of that, and we do that with two different methods. One is DTS, and the second one is DAS. So with DTS, you can actually get a warm back, and through warm back, you can see where your stimulation or where your injection fluid went into the rock, and kind of pinpoint what clusters are taking in the most injection fluid. The second form of that is using the DAS data. And with DAS, you use velocity. So with velocity, you kind of get a flow rate. And as you're leaving the wellbore, going into the reservoir, your flow rate starts to decrease more and more and more. And with that method, you can kind of also pinpoint where your fluid is going into. And if you have any large intake zones, such as in this example, you have a large intake zone here and here, you can easily pinpoint that with acoustic data. The last part to the injection illuminator is if you have an injector and you are kind of worried about its integrity, that's something that we are able to help you with. So we would go down into this well, you would inject, and we would watch to see what exactly is happening. So in this particular case, they had a blockage in around this area of the well, and a huge part of that lateral was not taking fluid, and you can see in the sketch right here where we're in this in the main wellbore, the fluid is actually going down the lateral well and going in through the rock and back into the main lateral well. So definitely something that we can pick up for you guys as well, any kind of injector integrity issues. And that's all I have for today. I hope, I really want to thank everyone for joining, and I want to pass this on to Henry for hopefully some discussion and questions.
Thank you, Ahmed. We'll start the Q&A session. Apologize, we kind of ran over on our time commitment. I know Craig has a hard stop, so Craig, thanks for joining us. Those of you that can stay on, you're welcome to stay on. It is recorded and will be available on Ziebel's website. So I'd like to start off with a question for Craig, since he has to leave here at 10 a.m. and Ohm too. In your experience with unconventional optimization, how mature is the industry in terms of the diagnostics and also completion designs?
Okay, well, I'll get to answer one question before I head off. I think that we're getting more and more information, and maybe we're in the I don't know if we say that in the middle phase of understanding. I think especially when it comes to to cluster spacing and things like that, the industry has done a lot of field-based experimental work to help us understand that, and just field data gathering. So I think we're pushing the limits of being able to to increase productivity using tighter and tighter cluster spacing. And I think that we're now getting a lot more information on cluster efficiency and uniformity, the type of data that Ziebel has provided, helping us understand how many clusters are actually producing, has been really key to our optimization efforts. I think that the real question going forward is this issue of well spacing and drainage area. I think that's what the industry is struggling with most, especially in this low price environment. So I'll turn it over to Ohm and see what he has to say about that. And again, I appreciate the time and you guys inviting me, but unfortunately I got to head off to another meeting. Thanks.
Thank you, Craig.
Yeah, for me, I think it's if I want to compare that to like an age of a person, I think we're in a teenager age type of phase. So you can see that we run a lot of diagnostics. It's like we having fun going out and try to do all this cool diagnostic data, but we still don't know exactly in some of the areas. So one thing I agree with Craig, that we're in a medium phase, or I would call it a teenager phase. At this point, we run a lot of cool stuff. But a lot of these stuff probably is going to be based on the basin specific. So the data I show you, it might work in the Bakken area, but you probably need to do something similar or additional data to work in Permian or Haynesville or some other assets there.
Thank you, Ohm. And I like your analogy to age. I think we can all relate to that. So thank you. So a question from Jose Rodriguez. Thanks, Ahmed, for your presentation. Does the Illuminator give real-time info?
Yeah, like I said, we developed that here just recently, so we can definitely get you guys a real-time information during Illuminator. I do want to be specific, though. We cannot be in the well that you are fracking. We can be in the well adjacent to the well that you're fracking, though, and give you real-time feedback on what's happening in the, if you have any FDI events or if you have any any kind of microseismic events as well.
Great. Thank you, Ahmed. Next question is from Blake Fortin. For camera, what determines a cluster to be efficient? Is it efficient if a hole is measured to be larger than 0.3 inches or the diameter you use? Unstimulated hole size, is there a minimum amount of erosion that needs to be efficient? So that sounds like a really good question for Ohm, maybe?
Yeah. Yep. Very good question. So it's very important to measure the effective clusters for the camera because you don't know what production is coming out from it. So in this case, we only look for holes that has been eroded. That's why our total clusters or our total holes eroded is very high. So I would say camera is a very good tool to look at heel-to-toe bias. But that's why there's one section in my conclusion that says there's additional work needs to be done to understand the correlation between camera data and fiber optics and injections. Again, bigger hole doesn't mean you get more production. Okay,
thank you. I think the next question probably is another Ohm question from anonymous attendee. Why haven't you run the production logging PLT to validate the fiber optic readings? Why haven't you run the chemical tracers?
So chemical tracer will run. Started with that one first. We ran chemical tracer. However, it's not relevant in this understanding of cluster efficiency. So that's why we did not show. Production logging we did not plan to run. I think just the budget and we believe that you guys product can provide us with the production profiles.
Great, thank you. Next question is from Leopoldo Sierra. I think that the post-frac step rate is really affected by the proppant placed in fracture and around the wellbore, and it could not be used to compare with the pre-frac step rate.
Sorry, ask that question again. Sorry, I'm looking at the question.
Yeah, I think it's a comment, maybe more than a question from Leopoldo. I think the post-frac step rate is really affected by the proppant placed in fracture and around the wellbore, and it could not be used to compare it with the pre-frac step rate.
Okay. The way I look at it is I'm looking at the change in between the pre and post. So that's for me, as long as I can show that I prove that I have high cluster efficiency throughout. I'm sorry, high limited entry pressure throughout. I prove it with the Ziebel as well. So that's clearly show that means something.
Well, thank you, Ohm. I guess I have kind of a related comment or question around that. Did you see or did you think that the step rate at the end of the job, it looked like your pressure was actually higher at the end of the job on step rates? Do you think that you lost some clusters because of proppant bridging or screen outs?
We know for sure we didn't get the actual well screen out, but it could be that we have some perforation screen outs that in those stages. But again, want to caution looking at the number of holes for step rate test. I would rather use fiber optic data to help for cluster efficiency than using step red test.
Okay, thank you. This question is from Mike Curry. Has anyone done a long-term study on the XLE about risk of perf clog to plug parts, etc.? With such minimal amount of perfs could add in risks.
Long-term study, I never studied that one yet, but one of these three wells that we did were about 1.5 years old, and the productions are right in line with the normal, even better in some wells, right in line with the normal injections. Normal limited entry pressure wells. What's the second question is the plug parts? The risk of
anything that could just plug up. You know, if you have low number of perforations in in a cluster, or anything that could plug up that perforation from producing, I think is the question.
Yeah, we have not seen that, to be honest with you. I mean, everything it's going good. Actually, XLE is our current standard design at the moment. So we design all our wells at XLE. We're actually pushing the boundary as well to go into a lower and lower number of holes.
Okay, sounds like you're still pushing the limits. The next question, the anonymous attendee, can you see perforation erosion from fiber strain data? Anyone want to take that one?
Ahmed?
Can you see perf erosion from fiber strain data? I would say we haven't explored that. I'm not going to say, you absolutely can't or you can. I know you can probably try to interpret, your amplitude if you actually knew that it was, how much fluid you pumped and sand you pumped in each one of those zones. You actually knew the diameter. You can probably do some back studies on that, but we have not done anything like that on surface to kind of give you that answer. So I would say currently the answer is no.
Okay, thank you, Ahmed. Next question, Leopoldo has another question. Can you comment about the correlation between the completion efficiency values you are showing and the production distribution? So that's the first part. Then a comment, in a long horizontal wellbore, you're dealing mainly with a transient flow for a long time. And this means that the flow distribution can change in time, and is not related to the quality of the stimulation.
Very, very good point. So basically, that's why Craig did another project with the permanent fiber. So the Ziebel technology, we use it as snapshot in time. So we have one pad last year as well that we actually came back and run it twice to understand the change in the transient flow in the wellbore. So we want to understand if the time goes by, how things change within the wellbore. So we did that as well. So yeah, your comments, we actually planned for that already. Can you comment about the correlation between completion efficiency value you are showing in the production? Completion efficiency. So that the first question is the correlation between completion efficiency value you're showing the production distribution. So I'm going to take a stab on this one. So basically, our completion efficiency values and the production distributions really, I would say they correlated, right? So you see that it's showing higher production cluster efficiency. I'm sorry, yeah, cluster efficiency, and also we show that we have higher production as well. So in this case, it's correlated in that case.
Okay, thank you. I apologize, my computer had a glitch, so I'm not able to see the questions. I think there's several more questions, so I'm going to turn that over to Mike Sparacino.
Sure. And
let him finish up on answering, responding to the questions.
Yeah. The next question we have is directed towards Ahmed. You mentioned the differential acoustics. Are you talking about low frequency strain data from the DAS?
Differential acoustics can actually be applied to all ranges of frequency. So yeah, we can do that for low frequency. We can do it for high frequency. It's basically a time step where you're taking the amplitude from time step 0 and subtracting it from the amplitude of time step 1 across one depth. So that's what we mean by differential acoustics.
The last one, it's actually to Ahmed. How is the carbon rod different from other fibers? What's the difference?
Yeah, that's a good question. So carbon rod is a dip-in technology. It can carry actually the actual carbon rod is the conveyance. It's not the fiber itself. So the carbon rod itself is being the conveyance is different than most technologies, as it is it's very small. It's only 0.6 inch in OD. It can carry 6 fiber optic lines in it. So we actually have 4. It's only 5 fiber optic lines now. It has 3 single mode and 2 multi-mode fibers. The multi-modes are for DTS. The single modes are for DAS boxes if you want to run more than one. And also the ability with the rod is you can actually push it. Unlike wireline, you can actually convey this rod without a tractor. And if you have a tractor, you can kind of assist the tractor to get it all the way to TD. It's actually a very good tool to run with a tractor job. And if you're talking about the actual fiber within the carbon rod, it's 400 degree F rated fiber. It's it can measure. It's not. It's just like any other fiber. It's not anything special. But the carbon rod is definitely the patented technology that fiber down the hole.
Thank you. Ohm, do you have any closing comments before we close this out?
No, for my part, I just want to really show that the XLE is working well, and it was able to save us a lot of money. So with these interesting diagnostic tools from these guys from Ziebel, I mean, we were able to help. They were able to help us achieve that goal. So thank you, Ziebel, for that, really. And for the comment with Ahmed on the tractor, we plan to run another 2 wells with them again in the next coming month here.
All right. Thank you very much.
Yep.
Again, I'd like to thank all the panelists, Ohm and Craig and Henry, Ahmed, and then Rob for helping us here. We really appreciate everyone's participation. I know we ran over, so I appreciate those that have been able to hang on for a few extra minutes. We have recorded this. We will have this online on the website, and we will send out a link to those that are registered as well, so that if you missed some of it, some of the questions and answers, if we haven't got to some of your questions, we will, if you sent those into us, we will make sure that those are answered. Again, thanks everybody for participating, and we look forward to seeing everyone again in the future. So thank you.
Thanks, guys. Appreciate y'all. Thanks, Ohm.
Thanks, guys. Bye.